So today, um, we've got a new problem set. Problem set 7 is right here. This this is the last problem set of the semester. You will end up seeing those kinds. You'll end up seeing some of those kinds of questions on the final exam. Remember that the final exam is cumulative, which means that you will basically see everything from the class on the final exam. Um, in terms of what to expect for that, I'll prepare a review. I'll probably give you guys that review on Monday, so that you have a little bit over a week to go over that exam review. Um, and yeah, I mean, you've basically already seen almost everything that's going to be on the exam. Um, it would have covered everything that we've done went up to lecture 13. So it'll just be the next couple of lectures will be like the only new stuff that you'll see. And so we had kind of already started on this conversation with the class that we had right before the exam. That was where we started talking about these nuclide production and destruction equations. And today we're gonna like review um whoops, we're gonna review what we talked about um on lecture 14, and then we're going to use that understanding to get into the topic for today. Last time we kind of outlined and started deriving what these production destruction equations look like, and this time we are going to start solving them, and then we're going to start applying them to some important nuclides of interest. The one we're going to talk about today is samarium 149, which is a very important neutron poison. Um, Before we get into it, I just wanted to like give kind of like a timeline for the rest of the semester. So today is Wednesday, the 23rd, 22nd. Thank you. And so today we're doing lecture 15. On Monday, we'll do lecture 16. That's also when I will post the final review. Normally, we would have a help session on Tuesday, but I'm going to be out of town basically like the rest of next week. So, in terms of that help session, what I think we should probably do is try to find a time to meet for that help session before Tuesday. So like I don't know what y'all would prefer, like if y'all would prefer tomorrow or if y'all would prefer Friday. Um, I wanted to do another help session, mostly focused on the project because like basically if you think about the project, that's going to be due on the 3rd, at midnight. So that was kind of one of the things I wanted to kind of field from y'all is if y'all had preference on when we would do that help session. Because basically, since I'm going to be gone like all of next week, I'm not going to be here physically to be able to do the help session. If you guys have questions during that time, definitely like shoot out an email. I will have my computer and I will have the ability to respond to questions via email. I just won't be here physically to do the help session. So if y'all had preference on doing that help session Thursday or Friday or even like Monday after class, I know that like going through class and then having the help session might be a lot, like just in terms of like time. But basically I was kind of hoping that we would do a help session just before this Tuesday so that we could like have dedicated time to talk about the project. Yes. No, so it's going to be asynchronous. Basically, what I'm going to do for the 17th is that I'm going to post the video. I'll also, so like whenever my preference, I guess, would be that you kind of just like I'll post that video, you could watch it at your own time, and then when I post that video, I'll also post a quiz on Canvas, and that quiz will have some questions that you can do based on lecture 17, also possibly based on some stuff from lecture 16, and then you'll just be able to do that on your own time, submit that on Canvas by the end of that day. Yes, that'll be the last quiz. So that's how the 17th will look, and that will be our last content for the semester. The 8th, August 3rd is the last day of class, like the last full class day. So that we'll have covered everything at that point. So on the 3rd, we'll mostly just be talking about reviewing for the final exam. We could also do last minute project help on that day as well. Um, I think this day is probably more helpful as like kind of a help session in terms of a combination of final exam questions and project questions. I'll briefly review, but like I didn't really want to spend the whole time reviewing just because I felt like I could repeat things that I've already told you, but y'all have the recordings, y'all have the notes. So it's my opinion that the 3rd would be more useful in terms of like it being kind of like a help, like maybe 20, 30 minutes of me talking and reviewing, and then spending the rest of the time answering questions that y'all have either about the final or about the project. Maybe even more focused on the project on that day because we'll have our Tuesday help session the day before the final exam. So because the project will have already been turned in by then, if you have questions about the final exam, that would probably be the things that we'd be talking about on Tuesday. And then the final exam is on the 5th here from 1 to 3 p.m. So yeah, that's kind of like the timeline for the rest of the semester. Do y'all have any feelings on when would be a good help session before this Tuesday, the 28th? Thursday? Okay, okay. Raise your hand if you vote for Thursday. Two. Raise your hand if you vote for Friday. Two. Does anybody want to? Okay. We 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 could do one on Monday. Would before class on Monday or after class on Monday be better? Before? Okay. Yeah. Okay. If if Monday is good, then let's do Monday. Let's say like 11 to noon. Is that okay? Because or maybe 10 to 11. I just wanted to give some time between the review and the class so that if like we wanted to like get lunch or just have a little break. Oh, do you guys have heat transfer? 9 to 11. Um, okay. I guess we could do it together before class. We could even do like a little pizza party. I could order pizza and then we could just have a kind of combo lunch and help session. Okay, so then let's shoot for that on Monday. Let's say from noon to 1, and then also give us like a 20-minute buffer in between that and coming here for the last for that lecture on the 16th. Okay, and I'll send an email out about that just to let everyone else know. But okay, sounds like a good plan. So yeah, that's just like some logistic stuff I wanted to talk about, and then I want to just kind of review some of the things that we went over last time. And so with the stuff that we're talking about right now, with these like production and destruction equations, this is mostly changes to the reactor state due to fuel burnup. Basically, the fuel being consumed or depleted as the reactor operates. You've got like uranium 235 and uranium 238, and you put that in the reactor, fissions happen, which means that fuel gets consumed and other things get produced from the fission events. And it's the fission products that get built up from your fuel being fissioned. Those fission products um, you basically get everything on the periodic table from your fission products. And some of those fission products are really important in terms of what they do to our reactor, in terms of having very high absorption cross sections. Xenon 135 is one of those isotopes. Samarium 149 is another one. So, yeah, that's like kind of the main things that we're talking about right now. These are more like intermediate and longer term questions of what happens to our reactor over like days to months. And so in terms of like what's happening over a longer period of time, that's mostly based on the depletion of our fuel. And as a result of the fact that these in terms of like when we think about what happens with our fuel being used up, when our fuel is being depleted, other things are being produced, and those things that are the fuel going being used up reduces our K effective. It reduces the reactivity of the system. And those fission products being built up, some of them are very absorbing, also impacts the reactivity of our system. And those new materials, like new fission products that are poisons that get built, those affect our absorption characteristics, which ends up affecting like our multiplication factor, and it also ends up impacting our flux. So the flux changes as the nuclides in our reactor change, and that kind of complicates our calculations because if you want to know what your nuclide concentrations are, they depend on the flux, but the flux also depends on the nuclide concentrations. So the flux and the nuclide concentrations are coupled in that sense. And the simple way that we can handle depletion problems is by assuming that that flux, our energy dependent scalar flux, changes slowly over time. So we can kind of take our energy dependent flux and approximate it as a constant over some like depletion time step. And then we can analyze the reactor as it goes. We can treat that flux as constant over that time step, do calculations based on a constant flux, which kind of removes that coupling. And so that approach, when we approximate the flux as being constant with time over like a time step, that's the adiabatic approximation. And that's what kind of allows us to analytically do depletion problems. The way that that works is that at time zero, you're going to know what your reactor looks like. That means you're going to know what your initial nuclide concentrations are. And you're also going to know, if you know your nuclide concentrations, then you could use like diffusion theory to predict what your flux looks like at the initial time step. And then once you know what that initial flux is, then over the first time step, you can treat that flux as constant, and you can use your production destruction equations with that constant flux to predict what your nuclide concentrations become at the end of that time step. So you'll have a constant flux over the first time step. The flux is constant. You'll use that constant flux to predict, using production and destruction equations, what your nuclide concentrations are. And then once you know at the end of that first time step, once you know what those nuclide concentrations are, you could then go back to diffusion theory, use the new concentrations and new kind of like reactor makeup to then recompute what your flux is at the end of that time step. And then you can use that new flux as a constant over the subsequent time step. And you would have this repeating process where you treat the flux as constant, you recompute your number densities, which allows you to recompute your cross sections, and then you use the new concentrations to compute a new flux, which you then treat as constant over the next time step. So that's kind of like the numerical approach that we use with this adiabatic scheme. Um, Ultimately, what we want is an equation that says for some given nuclide in our reactor, how does it evolve with time? And the way that we did that is using conservation. And those conservation statements are just mathematical statements that are basically differential equations that say the rate of change of that concentration equals all the ways that that nuclide can be gained minus all the ways that that nuclide can be lost. And when we're talking about production and destruction equations, the losses and the gains are either going to be due to decay, due to neutron capture, or to fission. And depending on what nuclide we're talking about, these mechanisms could either be a gain or a loss. And so we kind of talked about, we kind of revisited what these different reactions looked like, and we went through the thinking of like, what does a fission reaction look like to realize that if we're talking about some fuel nuclide like uranium-235, then that uranium-235 absorbs a neutron, fissions, and produces fission products. And so for like a fission reaction, the the fission of U-235 is a loss of U-235, and fission is a gain of our fission products. Similar thing with capture, that some nuclide like uranium-238 could capture a neutron, and then in capturing that neutron, it could become something else. And so that means that for U-238, capture might be a loss, whereas for the things that come after the neutron gets captured into U-238, what we would call transmutation products, those things are a gain due to capture, whereas for U-238, it would be a loss. And then decay is the other one. Lots of these nuclides in our reactors are radioactive, so they will decay. As a nuclide decays, it might produce a new isotope. That isotope might be radioactive, so it would decay. And so like for isotope Xi, its decay rate is a loss for it. Whereas for isotope Xj, the decay of Xi is a gain for isotope J, but then J is also radioactive, so it could decay, and then its own decay would be a loss. So production and loss rates can be due to fission, capture, and radioactive decay. Um, in terms of like getting a more detailed equation, we wanted to make our equations very general, and so we wanted to be able to consider that our reactor might have different regions, like it might have fuel and cladding and moderator. We want to consider all the different nuclides that we're interested in keeping track of. So all of our fuel nuclides, all of our fission products of interest, especially any fission products that have high absorption cross sections. We want to be able to track those different nuclides. And we also, a lot of our scalar flux is energy dependent. Our cross sections are energy dependent. So we have different groups, energy groups over which these reactions occur. And then we're ultimately interested in knowing how do these concentrations change with time. So then we can also talk about these quantities at different time steps in our problem. And we introduced indices for these different aspects of our problem. So we used H for like a region index for the different number of regions in our system. We used K as the nuclide index to keep track of all the different nuclides that we are interested in tracking. We kept using little g as a group energy group index, and we use a capital S for the time step index, which basically just says at what time step are we in our problem. And then we kind of broke our different nuclides up into I, Z, and J, where I were the fissionable nuclides. So like if you have uranium-235 or plutonium-239 in your reactor, those we use an index I. Any transmutable nuclides, a nuclide that could absorb a neutron and then produce something afterwards, those transmutable nuclides had an index Z. And then J was the decaying nuclide index. So any J nuclide that decays might produce the nuclide K after it decays. And so we used those ideas along with conservation to write these production destruction equations. And it might look complicated, but all this is a conservation statement. And in this case, K is the nuclide that we're keeping track of. H is the region index, and then S is the time step index. So this is saying the rate of change of the nuclide K in region H at the current time step capital S. So this is the rate of change of the nuclide K. And then anything that's positive on the right side of the equation is a gain mechanism for the nuclide K. And anything that has a minus sign in front of it is a loss mechanism for the nuclide K. And so if you see these first two terms, notice that there's a scalar flux, there's a number density, and then there's a fission cross-section. So if we were to look at those three terms together, flux times number density times a fission cross-section, fundamentally, what kind of quantity is that telling me about? Perfect. That's just the fission rate density. And then we've got this extra multiplier up front, this yield from isotope Y to K. And that's just a multiplier that we put on our fission rate density to say when isotope I fissions, what fraction of those fissions of isotope I produce the isotope K that we're trying to keep track of. And because we're using the adiabatic approximation, when we're trying to get what our concentrations of nuclides are at the time step S, we use the flux being constant at the end of that first time step. So that's why we have S minus 1 for our flux terms. That's a consequence of the adiabatic approximation, where we're using a constant flux from the previous time step to compute what our concentrations of our nuclides are over the current time step, big S. So this first term is just a fission production density. Notice that the second term also has a flux times a number density, but then times a capture cross-section. So that's just the capture rate density. And then there's a multiplier on the capture rate density, which says this is like the yield. This is like the capture yield, which basically says what fraction of captures of isotope Z produce the isotope K. Because if a nuclide absorbs a neutron, it might not always produce the same isotope. It might have multiple it might have multiple paths that it goes through after it captures something. That was kind of like what we were showing here, where this nuclide was capturing a neutron, and it might gain one to its atomic number if it emits a gamma particle after that capture, or it might spit out an alpha particle, in which case its atomic number goes down by three. So different capture reactions can technically produce different nuclide. This is kind of like saying the fraction of captures in isotope Z that produce the isotope K that we're keeping track of in our equation. And then this last one is we've got a number density times a decay constant. So that product right there is like a decay rate density. And then that decay rate density has a multiplier on it, which says these are like the fractions of decay of isotope J that produce the isotope K that we're keeping track of. And so the index I here is for all of my fissionable nuclides that are attached to this fission cross-section in our fission production term. The index Z is for all of our capturing, all of our transmutable nuclides that could capture a neutron and produce the isotope K. And then J is the decaying nuclide index, which is saying this is all of the decays of isotope J that could result in the production of the isotope K. So those are all the production mechanisms for the isotope K. And then these are the loss mechanisms of isotope K, where this is a decay rate density for the isotope K. Notice we have a lambda K and a number density of K. If K is some radioactive isotope, then that is the rate at which it is lost because it itself is radioactive and decays. And then this is like a absorption rate density for the isotope K. We've got a number density for K and a micro cross section for K, absorption cross section for K, and that's because we have an absorption term here because basically we've lumped the capture term and the fission term together because the capture plus the fission cross section gives us the absorption cross section. So that's fundamentally all this is saying is rate of change of this nuclide equals the way that it gets gained due to fission, due to capture, due to decay, and then the ways that it is lost from decay and the way that it's lost anytime it absorbs a neutron. Yes. Oh, um, yeah, good point. That it's almost like I just didn't have enough room to continue the equation. So yeah, that is not good point. Right? Oh, I need to plug this in. Yeah, that minus, it's not a double negative. Yeah, that it's almost like this should just it's almost like that should just not like yeah, basically just ignore that guy. Um yeah, these were all of our production terms and those were our two loss terms. Same thing here. And so that's like the most general way that we could write these production destruction equations, but we could also simplify them a little bit. If we do a one group approximation, then little g is just one. And if there's one group, then we can just drop the group g superscripts that we have. And also, if we use a one region reactor approximation, then there's only one region H. So then we can also drop the group H superscripts, and then our equations would look a lot nicer with just less stuff going on. But fundamentally, it means the exact same thing. And so what these equations are a coupled set of first order differential equations with constant coefficients. And they're coupled because the nuclide K that we're keeping track of ends up depending on all of these other nuclide concentrations. The concentrations of my fissile nuclides would be the Ni, the concentrations of my transmuting nuclides would be Nz, and then the concentrations of our decaying nuclides would be Nj. Um, and so that was kind of the starting equations that we have. We can simplify them a little bit more by the fact that like if you think about how many nuclides are actually formed in a reactor, K might be like 100 or 200. There's like lots of nuclides that get produced from fission, but a lot of the things that get produced from fission don't actually impact our reactor characteristics all that much. So what we can effectively do is reduce the number of groups that we have to keep track of by just lumping a lot of our fission products together. And so that's the idea behind these pseudo fission product yields is that we can take our all of our fission products and group them together such that instead of having like 100 fission products, we just lump them all together into one group of pseudo fission products. And so this Y with a tilde is the yield of our pseudo fission products of type I that produce the isotope K And the yield is basically just the sum of the yields of all of the individual fission products. And then we have a absorption cross section for our fission product. Our pseudo fission product absorption cross section is basically just like a weighted average of our absorption cross sections to the yields. So this is mathematically how you could group all of your how you could get an effective yield and an effective absorption cross section. And this is done in such a way that the pseudo fission products have similar properties to what all of those individual fission products would do if you treated them separately. So with that as like our starting point, we then started to look at analytical solutions under like a simplified model where we're only keeping track of 9 different nuclides. So K goes from 0 all the way up to 8. The first isotope 0 is going to be our fissile nuclide that we're starting with. And then we're going to consider a bunch of the remaining isotopes 1 through 7 are going to be isotopes in the fertile to fissile conversion chain. And then we're going to group all of the fission products together into a pseudo fission product, which was number 8. And we used one group and we used one region. So this is a table of what those isotopes would look like for 2 simplified models. This is a uranium-plutonium cycle, and that's like more common because you don't really see the other one is a thorium-uranium cycle. None of the reactors in the United States use thorium for power production, so we're gonna more focus on what we do more in the States, which would be the uranium-plutonium cycle. So U-235 is your initially loaded fissile nuclide, and your fuel is some combination of U-235 and also U-238. So U-238 is the fertile nuclide, which is isotope 1, and these are all of the nuclides that come out of this fertile to fissile conversion chain. 6 and 7 also end up coming out of this process. And then material number 8 is all of our pseudo-fission products that we group together. So this is kind of showing what that like in a picture, what these chains would look like. So U-235 is like our initial fissile material. You put some amount of uranium-235 in the reactor, and then you turn the reactor on. And as the reactor operates, U-235 could fission, in which case it's going to produce some fission products. U-235 could also capture a neutron, but not fission. And so that's going to result in U-235 capturing a neutron and then becoming something else. But ultimately, the something else that it produces, we don't really pay too much attention to. So that's the way, if you see an arrow going away from a nuclide, those are losses for that nuclide. And if you see an arrow going into a nuclide, those are gains for that nuclide. So then if we look at isotope 1, which would be uranium-238, it's kind of the same story as U-235 in that it could fission and produce fission products, or it could capture a neutron, go through a beta decay, and then become something else. And when uranium-238 captures a neutron, it actually goes through 2 beta decays, but eventually it produces plutonium-239. And plutonium-239 itself could fission, in which case it produces fission products, or it could capture a neutron and it would become plutonium-240. So if you look at isotope 2, plutonium-239, it has a gain mechanism due to the capture of U-238. It also has a loss mechanisms due to fission and itself capturing a neutron and becoming something else. 240 is kind of a similar story. It gets produced when plutonium-239 captures neutrons. It gets lost when it fissions or when it captures stuff. And then you get plutonium-241, which could fission. It could capture a neutron. Or plutonium-241 is radioactive. And like a lot of these nuclides themselves are radioactive, but if their half-lives are really, really long, then we don't really need to consider them in these production destruction equations. Like, the half-life for uranium-235 is like on the order of like, I don't know off the top of my head, it's like hundreds of thousands or millions of years. So much, much longer than our time steps that we're considering, those decay constants. So a lot of these things might be radioactive, but we just don't include their decay in the calculation because it's effectively negligible. But plutonium 241 has a decay constant that's large enough that we do consider it. It could decay and produce americium 241. Americium 241 could absorb a it could absorb a sorry. Oh, okay. Americium 241 could absorb a neutron and basically become another thing that is the same as the fission products that we would be keeping track of. Um, and so that's kind of what happens with americium 241. And then, so fundamentally, the story is that if there's arrows going away from something, those are losses due to different mechanisms associated with that isotope. And if there's an arrow going to it, then those are gain mechanisms, again, associated with whatever processes are occurring. And so K equals 8 are all of these different fission products. Notice that each of these different isotopes could fission and produce a fission product. Those fission products all get grouped together, which is K equals 8. And so if you think about setting up actual mathematical statements based on that chart that we were just looking at, then that's kind of what we're showing here. So isotope 0 was uranium-235, and uranium-235, if we kind of go back, uranium-235 was lost due to fission, and it was lost due to capture. And so if we look at this term for uranium-235, we've effectively grouped the capture and the fission together to give us the absorption rate. Because basically, anytime that uranium is absorbing, 235 is absorbing a neutron, it's being lost and it's becoming something else. If we look at the arrows going away from 238, it could also be lost due to fission. It could also be lost due to capture. And the fission plus the capture is just the absorption. That's why for isotope 1, it is lost due to absorption. This is basically the absorption rate density of this isotope, which is resulting in it going away. This is the absorption rate density of isotope 0, resulting in it going away. And then if we look at isotope 2, it has a production due to uranium-238, which is isotope 1 capturing neutrons. So it's going to have a gain term that looks like the capture rate density of U-238, and then it's going to have losses due to fission and due to capture. So if I look at the equation for isotope 2, it has a production term that looks like the capture rate density of isotope 1, which was the uranium-238, multiplied by this gamma factor, which says of what fraction of captures in isotope 1 do I produce this isotope 2. And then again, it's lost due to capture and it's lost due to fission, and we group the capture and fission together as an absorption. And you could go through every other nuclide in that chart. You could set up these conservation statements based on what are the gain mechanisms and what are the loss mechanisms. Um, isotope 8, which would be our pseudo-fission products, there's a bunch of terms here because we're basically accounting for the fissioning of all of the different isotopes that we were looking at in our chain that end up producing these pseudo fission products. And so these were like the individual equations for each isotope, and then you could, based on the form of these equations, you could group them all into a matrix. And so that's what this is showing. Um, And so hopefully this just helps us illustrate that these concentrations of these different nuclides, it's a coupled problem, and that the concentration of one nuclide might be required to predict what's happening with another nuclide. And so what we wanted to eventually do is actually start coming up with analytical solutions so that we can predict over some time step how do the concentrations of these nuclides change. And so each of these equations is effectively a differential equation, and they're differential equations in time. And to solve a differential equation, we need either initial conditions or boundary conditions. In this case, because the only variable is time, all we need is an initial condition. So effectively, to be able to solve these equations, we need to know the concentrations of these nuclides at the beginning of our time step. And so mathematically, what we're going to say is that we need to know the concentration of nuclide K at the start of our time step S. And the start of our time step S corresponds to the time t at S minus 1. So we need to know the amount of nuclide K at time step S at the start of our time step. And mathematically, the way that we would write that is n k comma S minus 1. So this is just saying we're trying to predict what's the concentration of our nuclide um, over this time step delta t. And that's going to be based on the value of that nuclide concentration at the start of that time step. The time step starts at TS minus 1. It ends at TS minus 1 plus delta TS, where delta TS is the time step. So this is basically just like saying we have some amount of this nuclide K at time t equals 0. It's just that we're starting not at 0, but at TS minus 1. So therefore, that's what this subscript S minus 1 is saying. Just the amount at the start of the time step. And so this was the if we're this is for the K equals 0 nuclide. So this is the rate of change of nuclide 0 over this time step. And it's just due to this nuclide absorbing neutrons. And this is an equation that is analytically solvable. We've got a differential equation and we've got our initial condition. So if we wanted to solve this differential equation for eventually, basically what we're trying to get is some equation for the amount of this nuclide 0 at the over this time step S as a function of time. So the question is, how do we find that? What do we do with this differential equation to solve for the amount of this quantity? So if you guys had this differential equation, how would you go about solving it? And remember that we're treating the flux as constant over the time step. So this flux is just a constant. And we're also assuming that the cross section is a constant as well. It is gonna it is going to be an exponential. And the way that we would get there, though, is by hopefully realizing that this kind of differential equation is what we would call a separable differential equation. It means that we could separate it such that we have all of our things that depend on the concentration on one side and all of the things that either depend on time or are constants on the other side. So it's like we're going to treat this is almost like a fraction, and we're going to multiply both sides by dt, and we're also going to move this n0 to the other side. And so what we're going to have is, if we were to divide both sides by the concentration, we'd have 1 over n0s dn0s equals, and then we're going to multiply by dt. So we'd have negative phi at s minus 1 times sigma a 0 dt. So we're separating the differential equation. We're getting everything that depends on the concentration on one side and all of our constants on the other side with our dt. And once I get here, what can I do next? What would be my next step? You just integrate both sides, right? Perfect. So we're going to integrate this side and we're going to integrate this side. What do I get when I integrate 1 over n0s with respect to n0s? ln, right? It's going to be a natural log of n0s. And that n0s is a function of time. And on the right-hand side, I'm basically just integrating a constant with respect to time. And if I integrate a constant with respect to time, I basically just have this constant and then I pick up a factor of t, right? So this is going to say minus phi of s minus 1 times sigma a 0 times the variable t. And these were indefinite integrals. So when I integrate both sides, what else do I need? You need a constant of integration. So I'll say plus c. Perfect. And From here, what I need to do is I'm ultimately trying to get an equation for the concentration of nuclide zero. So how do I get this concentration by itself if it's inside of a log? Take the exponential of both sides. So that's what I'm going to show here. I'm going to exponentiate both sides. So on the left-hand side, I get N0s of t, because the exponential, if I do e to the power of this, then the e and the ln cancel each other out. And if I do e to the power of all of this, then I'm going to have on the right-hand side, it's going to look like e to the a plus b. And if you want to think about properties of exponents, which is that e to the a plus b is the same thing as e to the a, e to the a times e to the b. Perfect. So that's going to look like e to the negative phi of s minus 1 sigma a 0 times t times e to the c. And c is a constant, so e to the c is also a constant. So if you wanted to, you could basically just take this e to the c and replace it with just a constant c. So that so like just like what we were thinking is that that's going to look like an exponential, and it does. And the only real thing that kind of complicates finding this constant c is that our initial condition doesn't start at 0. It starts at ts minus 1. So like to evaluate what c is, I would use this initial condition, but I'm plugging in t of s minus 1. So when I plug in t of s minus 1 here, that is the amount of my nuclide at the time ts minus 1, which is this initial concentration that was given. And when I do it on the right-hand side, though, this exponential isn't going to go away. This exponential is going to have a t of s minus 1 right here. So ultimately, what my solution is going to look like N0s of t is equal to that initial concentration N0 at s minus 1. And then I'm going to have times the exponential of negative phi of s minus 1 times sigma a of 0 times the quantity t minus t at s minus 1. So I basically end up picking up this extra term because of the fact that this exponential doesn't go to 0 when I evaluate my initial condition. And also, you could kind of notice that if t of s minus 1 was 0, then this would say then this would become a 0, and then this t of s minus 1 would become a 0, and then it would look like the kind of functional form that we would expect if we were starting at 0 for time. But we're kind of writing this in a general way where s minus 1 could just be whatever the starting value of our time interval is. So even though things look a little bit complicated because of the subscripts, fundamentally these are still ordinary differential equations. They can be solved analytically. You just kind of got to be careful about what you're doing in terms of evaluating your initial conditions at like an arbitrary time instead of at time 0. Hopefully, is that okay? Do we have any questions about how we got through that? That would definitely be something I would expect us to be able to do, like possibly on exam. You'll have some practice doing this on the homework as well. So we just solved the k equals 0 equation, which was this guy right here, and we found that this was our general solution. If we wanted to go ahead and start solving the k equals 1 equation, notice that the form of these two equations is basically the same mathematical form. So if I wanted to write a solution for for nuclide 1, how is it going to compare in terms of the form for the solution for nuclide 0? Yeah, it's going to be the same, but just with a subscript 1. So it's basically that's what we can write. It's going to look the same, but with a subscript 1 instead. And I can't write. oops, instead of 0. So it'd be like n1 of s. This would be n1 at s minus 1, and then this would still be phi at s minus 1. This would be sigma a for isotope 1. So same governing equation, we basically would get the same functional form of our solution. Is that pattern going to hold for the k equals 2 or 3 or higher functions that we're doing? It's not. So this pattern will not hold for those. And the pattern won't hold because for all of the higher isotopes in our chain, we both have gain and loss mechanisms. Also, notice that like if I were to think about the equation, if I wanted to find an analytical equation for isotope 2, I could, but isotope 2, this is a couple differential equation because isotope 1, its concentration is a part of the equation for isotope 2. So I would need right here for N1 of S, I would need to take the general solution for isotope 1. I would need to plug, I would need to plug it in right here for N1 of S, and then I would have an equation that only contained N2 that I could solve for, but because this differential equation has two terms, it's no longer separable. So, do y'all know what would be the differential equation solving method that I would use to solve this kind of equation? Yeah, integrating factors. Perfect. It would be involving the method of integrating factors. And so integrating factors are a little bit more involved than doing separable differential equations. That's why in my slides, I haven't worked, I wasn't planning to work through all of the steps. Um, it is a good exercise to be able to do that. Um, I gave you some problems on the problem set 7, which would get you to practice that. What I would recommend when you're doing integrating factors is the resource that I always go to when I need to solve an equation using integrating factors is I go to Paul's online math notes and then I type integrating factors. This section 2.1 on linear differential equations is the resource that I go to. And this is a good write-up that kind of explains, this is showing what the governing kind of like a functional form is when you need to do integrating factors. So like this is the same kind of equation that we were just dealing with, where y is the thing that I'm trying to solve for. And my differential equation dy dt, my this dy dt is not just equal to some function times y. I have this function times y, and I have this extra time-dependent function that appears. So like if g of t was 0, then this is just another separable differential equation where I can move the p of t times y over, I could divide by y, I could multiply by dt, I could integrate both sides, and I would have a very easy time hopefully solving that as long as p of t was an equation that was easy to integrate. But this g of t being there is kind of like what we have here, where we have this n1 of s, because this n1 of s is going to be a function that depends on time. That's like an exponential time decaying function. So this term right here is like my g of t, and then this term right here is like my p of t times y. So, whoops. So the way that you solve a differential equation like this is by going through the integrating factor process. I also like Paul's online math notes because he kind of just jumps to this is what the solution is going to look like for y of t. And it's basically going to involve taking this integrating factor, taking whatever that g of t function is, and integrating those, and then also dividing by that integrating factor. And the integrating factor itself has an equation that looks like this. The integrating factor is just an exponential integrated with the p of t function. So I like to write my differential equation in the same form that we have here. I like to spell out what's my p of t and what's my g of t. Because if I can spell that out, then I've got equation 7 is my governing form for the y of t solution. And equation this equation right here, which doesn't have a number, but oh, yeah, this equation right, yeah, I guess it's kind of the same thing. But yeah, mu, the integrating factor, has this definition. So if I can identify P of t and G of t, I've got kind of like a plug and play form that I could use to solve those equations via integrating factors. And if you were to go ahead and solve those equations using integrating factors, what you have below here is the result that you should get. So this is what the equation for N2 of S would look like. And notice that things get a lot more complicated when you add multiple terms. So that's the form of the N2 solution. And for all of the remaining nuclides, you would have to do something similar. And the remaining nuclide equations are going to get more complicated because, like, if I wanted to go and solve for nuclide 3, I would have to plug that big solution in for N2 in right here, and then I would have to do another integrating factor on this guy, except now my G of t function gets a lot more complicated. Um, so analytically, oh, yes, Robbie? I probably, on an exam, if you do something with the result, here, oops, I don't know what I just did. They'll either be separable or they will require an integrating factor. Am I still recording? Okay, I'm still recording. So this is an example where I'm kind of thinking about things in a more analytical way, assuming that I have a flux that depends on time and I have a nuclide concentration that also is going to change with position and with time. So like we're imagining that N sub F is just whatever our initial fuel is, our fuel concentration. And we've got a absorption cross section for the fuel, and there's no other initial fissile nuclides or fertile material in the reactor. And so if I have this, if this is the concentration of my fuel in the reactor, then my differential equation for this fuel is going to say change rate equals gain rate minus loss rate. And so the change rate is going to say dNF of R and T dt. And that change rate is going to be gains minus losses. But this is my fissile nuclide. So there's no gain rates for my fissile nuclide. Like there's no way I can gain U-235 unless I'm like continually adding fuel into my reactor. So the only thing on the right side is a loss due to absorption of my fuel. So the loss term is going to look like an absorption rate density for this nuclide. So so I'm gonna have a minus sign, and the absorption rate density is my flux, which depends on position and time. It's going to involve my number density of my fuel, which depends on position and time, and it's going to involve the absorption cross section of my fuel. So that would be my absorption rate density, and that would be my governing differential equation for my fuel if I was treating my flux as a time-dependent function and my fuel as a time-dependent function. So this would be my governing differential equation, and if I wanted to solve it, I would need to know the initial condition for my fuel. In other words, I would need to know for my fuel at position R and at the initial time, which we can just call time 0, I would need to know what this looks like as some function of position. And notice that this is also just a separable differential equation. I could put my NF on one side, I can move my dt to the other side, I can integrate both sides. On the left, I'd be integrating over the concentration. On the right side, I'd be integrating over time. But the flux itself is going to depend on time. So in my solution, I'm going to have an integral of that flux with respect to time because I would need to know what that flux was as a function for me to be able to integrate it with respect to time. And there's a challenge here, which kind of illustrates the complexity of coupling your concentrations and your fluxes, which that is that if I want to know my fuel concentration as a function of time, I need to know my flux as a function of time. But my flux as a function of time is influenced by my fuel concentration. So this is like helping to illustrate the coupling of my concentrations and my fluxes. And it helps me realize that if I'm doing an analytical problem, then I can't determine either one of these independently. They have to be solved at the same time. So for equations like this, you can really only do it numerically if you want to actually deal with the complex coupling between your concentrations and your fluxes. Um, so the next thing I wanted to talk about is something called equilibrium depletion modeling. And this is like something that's really important to actual reactor operation and design. If you think about like loading up a reactor for the first time, you're going to fill it up with fresh fuel, and then you're going to turn your reactor on. And when you turn your reactor on, it's going to operate for a pretty long time. They're going to operate from like 12 to 18 to like 24 months, depending on where you are and what the design of the reactor is. And so you're going to run it over the cycle of your reactor, and then after that period of operation, you're going to take like the top off of your reactor pressure vessel. You're going to take those fuel assemblies and you're going to shuffle them around. And generally, what you would do is you're going to take the fuel assemblies that are on the outer periphery and you're going to move those more in. And then you're going to replace those ones that were kind of near the kind of midpoint to the center. And you're going to take the ones that were in the center and you're going to take those all the way out of the reactor and put them somewhere else. And then that outer fuel is going to be replaced with new fresh fuel. And so after you do this for a couple of times, you'll get to a point where you have what's called an equilibrium cycle. And with an equilibrium cycle, it means that if you're looking at the composition of your fuel at the beginning of your fuel loading, and then you run it for your operation time, and then you refuel it after the operation time is up. When you refuel it, the concentrations of your nuclides and your nuclide compositions look exactly the way they looked before you at the beginning of that previous cycle. So that's the idea behind an equilibrium cycle, is that your reactor state at the beginning of refueling looks the same at every time that you do a refueling operation. And that kind of supposes that you are running a reactor for a relatively constant, that for every cycle, you're running it for the same amount of time and you're running it for the same amount of power. Otherwise, you would end up depleting your fuel in different ways from cycle to cycle. And so these are like kind of the more complicated, like if you went to work at a nuclear power plant as a nuclear engineer, like specifically doing nuclear engineering, these kind of equilibrium cycle calculations would be one of the things that would possibly be your job. Um, and so, yeah, as you might imagine, that involves being very careful and deliberate and knowing in detail what your concentrations of your nuclides are looking like at the beginning of fueling, as the reactor operates, and then at the end of fueling. Um, the other thing that we kind of want to think about, also getting back into like real reactor operation, is that if you load a reactor up at the start of operation, then your fuel is the freshest at the moment that you load it into the reactor. And then as you run your reactor, those fissile isotopes get used up, the fuel gets depleted, and that means that the reactivity of your system constantly decreases because you're consuming your fuel. And so you can add in a feed source, F, with a vector. The vector F is a vector of sources for my different fissile nuclide and for my fertile nuclide, which basically represents like a production term that would appear in my differential equations, where like for the uranium-235, we'd be saying that it's lost due to absorption, but it's also gained if we have a feed source that's continuously replenishing the amount of fuel that I have in my system. And so yeah, that's what those F's are. It's the feed source. And this is what those differential equations would look like if you added a feed source, where F0 would be the source of uranium-235 if that's isotope 0, and F1 would be the feed source for isotope 1, which might be like uranium-238. And so if I think about these as a matrix, then the matrix form of these equations is going to look like D, N, K, S, dt, where this is a vector. And my vector goes for k equals 0 all the way up to 8. And that rate of change of my that change rate of my concentrations is going to look like some coefficient matrix that depends on the flux. So we'll say A at phi, sorry, it's supposed to be phi of S minus 1. Coefficient matrix times the column vector of my concentrations. So times my nuclide concentration vector, and then plus my feed source vector of k. And so like in this case, that goes from for k equals 0, 1, 2, all the way up to 8 in this example. So that's just how you could compactly write all of these equations as a matrix. And without the feed source, my fuel nuclides will just exponentially decrease as time goes forward. But if I add in this feed source, then it allows for me to obtain an equilibrium concentration of these fuel nuclides. And an equilibrium concentration, or the equilibrium case, just means that I'm getting to a point where the rate of change of my concentrations is no longer changing with time. So these derivatives, if I were to evaluate these equations in their equilibrium situation, that would be at a very long time into the operation where all of these derivatives are equal to 0. And if all of these derivatives are equal to 0, then I don't even have a system of ordinary equations, ordinary differential equations. I just have a system of linear equations, and those can be easily solved doing like linear algebra stuff, or even just solving the equations one by one to determine what the asymptotic or the equilibrium concentrations of these various nuclides would be. So we're talking about our fuel. We're imagining that when we put fuel into the reactor and then turn it on, our uranium-235 and uranium-238, something is happening to them. When I put uranium into my reactor and then I turn it on, what ends up happening to those fuel atoms? Does the fuel stay there forever? Or if not, what happens to it? Sorry? The fuel, well, yeah, so like the fuel pellet does all kinds of crazy stuff as the reactor goes. Those fuel pellets, if you look at them like at the beginning of operation, they're these like nice perfect cylinders, and then as the fuel gets used up, they start to swell. If you run them for long enough, they'll start to crack. Part of that is because in the fission process, these nuclei are splitting, and like when uranium splits and fissions, the uranium goes away and it produces fission products. Some of those fission products are gases. So you almost have like this solid where gases are getting built up inside it. And so that's part of why it causes the pellet to like swell up. But yeah, so that is true. But I guess I was just looking for like a more simple answer of that. The fuel is consumed. You could say it gets consumed, or you could say it gets depleted. And as the fuel gets used up, fission products get born. So if you were to imagine the number of uranium-235 nuclei that you have at time 0 when you turn the reactor on, that reactor might have a fission rate of like 10 to the 10 fissions per second. So that means every fission is using up a fuel atom. So you would have 10 to the 10 isotopes, atoms of uranium that are being used up every second. So your fuel is getting burned up or depleted, and that's and we use the term burn up in terms of like a nuclear engineering term to, I guess there's multiple ways that we can define it. One way is just a measure of how much energy was obtained or extracted from the fuel. And so if we talk about it in that first context of energy use, we use units of megawatt days per kilogram of heavy metal. So that's kind of definition one as a measure of how much energy was obtained from the fuel. So it's like energy obtained from the fuel per unit fuel loading. And then the other definition is the fraction of the heavy metal atoms that have fissioned. And if we talk about it in that context, it's just basically an atom percent. It's like, some percentage of our atoms have been used up. I think the first one is more common. And so we can use a symbol B with the subscript R for burn up. And this would be the average burn up with the overbar on top. And so if we think about the average burn up, it's megawatt days. And so if I think about megawatts, what kind of quantity has units of megawatts? It would be power, right? Because energy, so like 1 watt is is 1 joule per second, right? So joules would be the units of energy. And when I talk about watts, it's energy per unit time, which would be power. So the megawatts is like my fission power, PF. And then days, that's like a unit of time. That's like a unit of how long is my reactor operating. So I could say TF, and I'll define these terms in a second. And then we're dividing by the kilogram of heavy metal. And so I can just say by the mass of heavy metal. So that as an equation, like these are the units, that's how I could think of it as an equation. And in terms of these, with these terms, PF would be my fission power. And that's the thing that would have units of megawatts. TF, that is what I would call the time at rated power. Time at rated power. That's going to have units of days. And then the MHM is the mass of initially loaded heavy metal. Mass of initially loaded heavy metal. And that's in units of kilograms. So TF is defined in a particular way because the time at rated power is different than like the chronological time. Um, if you like have a reactor and you're turning it on, there's like a startup procedure. It takes you a while, like it might take you a couple of days to go from cold power to hot full power. So the time at rated power, like if it's an AP1000 reactor, that means that the fission power is like some number of megawatts, and it has a certain amount of time that it operates at full power before you have to like reshuffle your fuel. And so that's what that time at rated power is. It's like how long does the reactor operate at its full power that it was designed for. And then when we talk about the mass of heavy metal, we just need to be careful that that's only the mass of the fuel atoms that I have in my reactor. Like if I have a UO2 pellet, it's only the mass of the uranium in that fuel pellet. It doesn't include all of the oxygen as well. So that's kind of, there's some important things that we want to just make sure we're clear on because these units can get confusing and thinking, you could end up plugging in the wrong values if you weren't particular about what these are defined as. So the time at rated power is different than the chronological time. Um, when you think about startup, it takes some time for that to happen. So the power is based on like the fission power of the reactor. Um, if you think about how long that reactor operates at full power compared to the chronological time, how are those numbers going to compare? If I were to compare the time at rated power to the chronological time, which of those times is going to be larger? The chronological time is gonna be larger. So if I think about what my time at rated power is, the time spent at rated power is going to be less than the chronological time, less than TR. Because, if and that has to do with the fact that there's some time that it takes to start up, there's some time that it takes to cool down. So the overall time from like T0 when you first start making fissions happen um, to T final where you're like pulling the fuel out of the reactor, that's different from the time at rated power. It's not going to be at rated power for as long as the time that elapses from when you very first start making fissions happen to when you start to pull the fuel out. And in power production, you've probably heard this term, the capacity factor, and that is related to the difference between, or really the ratio between my time at rated power to my chronological time. In other words, the time at rated power is this capacity factor F times the chronological time. So like for nuclear reactors, they have a pretty high capacity factor. The capacity factor is anywhere from like zero point 0.9 or like around 0.95. So that means like 95% of the year the reactor is operating at its rated power. Um, so that's the definition. That's kind of how the capacity factor is defined. And yeah, just making sure that we're aware that when we say massive heavy metal, it's only the fuel atoms in our reactor. It doesn't include the oxygen if you have like an oxide fuel. And so if you want to talk about what the mass of heavy metal is, then you can use the density of your fuel to compute that. If you know if you know how much mass of like the overall fuel that you have, like if it's UO2, then you would probably know the mass of UO2. That's going to be like how much fuel is loaded into your reactor. And if you want to get the mass of heavy metal from that, you take your mass of your oxide mixture and you multiply by the ratio of the molar masses of your heavy metal to the molar mass of your oxide fuel. And if you multiply by that ratio, then it will convert the total mass into just the mass of the heavy metal that's there. So we can write our burnup equation because it has the fission power in there. We can also write it in terms of the power density. My power density is EF, the energy per fission, times sigma F times the flux. The flux times the macro cross-section for fission is my fission rate density, and the energy per fission converts that fission rate density into a power rate or an energy rate density, which is the power density. Um, and so if I think about an average burnup, that can be if it depends on the power, that means that I could also write the burnup in terms of the power density. And if I wanted to go from power density to power, what would I do with the power density to convert it into just a total power? Integrate over the volume, right? And if I want to talk about an average value, like if that flux, instead of treating it as a position dependent quantity, I just said, what's the average over the whole reactor? Then I could just multiply by the volume instead of having to integrate. So in that sense, then my power in the top is going to be EF times sigma F times the flux. That's like my power density. I'm going to multiply by the volume. And I'm going to write my time at rated power in terms of the capacity factor and the chronological time. And then in the bottom, um, what I would have is the mass of, I could write this as the mass of my oxide times the molar mass of my heavy metal divided by the molar mass of my oxide. So just kind of like using this definition right here to rewrite the mass of heavy metal in terms of the mass of the oxide fuel and then the molar mass ratio. And then notice if I have a volume up top, then what I could do is I could divide the top and the bottom by volume. And if I divide the top and bottom by volume, then this volume is going to cancel. I'm going to end up dividing this by the volume. And if I have a mass divided by a volume for this oxide fuel, what does that quantity come out to if I do mass over volume? That'd be the density of the oxide fuel. So then I could rewrite it like this. I would have EF, sigma F, flux, capacity factor, chronological time divided by the density of my oxide fuel times that molar mass ratio. Molar mass of my heavy metal divided by the molar mass of my oxide. So this is like maybe a more useful formula for burnup that you could calculate from some parameters that you are more likely to be able to have access to. So that's a very nice, simple way that we can hand calculate what the burnup is. And notice that the burnup for our reactor depends on the time that the reactor is operating, which is the capacity factor times the time at rated power. And in the US, if you look at like how much power we get from nuclear as a function of time, that graph has been like very slowly going up, even though we haven't really been consistently building new reactors. And the reason that the power that we get from our reactors has been slightly going up, even though we're not really building that many new ones, is because we've been coming up with clever ways to make our reactors more fuel efficient. And part of the way that we do that is by going to higher burnups. And if you go to a higher burnup, it means that you run your reactor for longer, which means that you get a higher capacity factor, and a higher capacity factor means that your burnup ends up going up. So that was the definition of burnup that we talked about. Here, the flux is representing like the average flux in the reactor. But we know that in reality, the flux is position dependent. Like if you think about the shapes that we talked about, like cubes and spheres and cylinders and rectangular parallelepipeds, then we know that for all of those geometries, the flux varies with position in the reactor, varies with position R in the reactor. And we know that for all of those shapes, the flux has a maximum value. And where's the maximum value of the flux for all of those one group diffusion approximations that we found? It's in the fuel, but like where geometrically, like if the reactor is shaped like a cylinder, where's the flux the highest? In the geometric center. Perfect. And that's the case for all of them. It's the max at the geometric center. So at the center of these reactors is where our flux is the highest. If our burnup depends on the flux, that means that the burnup is also going to vary with position. And if the flux is higher in certain places, that means that the burnup is also going to be higher in certain places. And if the flux is the highest at the center, that means that the burnup is also going to be highest in its center. So if you have fuel distributed across your reactor and you have different assemblies at different radial distances from the center, then the fuel that's in the middle is going to get depleted faster than the fuel that's like further away from the center. And that also goes along with the story of fuel shuffling and being careful about how we arrange the fuel in our reactor such that there's higher enriched fuel on the outside. And as you go into the middle, the fuel has lower enrichment. That lower enrichment fuel can still generate a decent amount of power because the flux is higher in those areas. And that allows us to get better utilization of our fuel. It also allows us to make sure that it allows us to keep our power profiles more flat. You don't want the power to vary considerably as you go like across the width of your reactor because from like an engineering perspective, it's more stress on your components to have temperature gradients. And so if you have a more uniform flux profile, you have a more uniform temperature profile, and that allows for your reactor to operate longer without having to do maintenance on it. When we calculate burnup, there is a product of the flux times a time interval. And in nuclear engineering, we kind of give the time integrated flux its own definition called the fluence. And apologies for this, but we use a capital phi for the fluence, at least historically. So the fluence is defined by definition to be the time integral, so integrating like from 0 to some time capital T of our neutron flux. By definition, that's what the fluence is. And if the flux has units of neutron path rate per unit volume per unit time, and we integrate that over time, it knocks out the time units. So the units of the fluence are just neutron path length per unit volume, which is the same thing as just saying neutrons per centimeter squared. That is supposed to be an N, even though it doesn't look like it. So that's what the fluence represents. The total path length per unit volume traveled by neutrons over this time interval, capital T. And if you think about your reactor having a relatively high flux, like 10 to the 13 would be around the value of a typical flux in a reactor, those neutrons are going to be impinging on the pressure vessel, like the steel lining of your reactor. And when neutrons interact with materials, they cause damage to those materials. And the fluence is a number that is very much related to the radiation damage caused by the materials in your reactor. In material science, there's a quantity called displacements per atom, which is basically like if you think about your structures as a crystalline lattice of atoms, then how many displacements do those atoms make per atom in your system? The fluence is directly related to that. And the displacements per atom is what relates to material damage, which over time causes things like radiation-induced embrittlement and stresses and things like that. And if this flux is constant over the time interval, then the flux no longer depends on time. The flux can just come out of the integral, and then we're integrating dt from 0 to big T. So the integral of that would just be the time interval t. So if your flux is constant, then this just looks like phi of r times that time interval t. All right. Um, so now that we've talked about burnup and we've talked about nuclide production and destruction equations, we can start applying that information to develop conservation statements for some nuclides that are of particular interest to us as nuclear engineers. We've already talked about fission reactions producing fission products, and pretty much all fission products that are born end up absorbing neutrons, at least to some extent. Some of these fission products have very high neutron absorption cross sections, and we refer to those nuclides as fission product poisons because they basically poison the neutron economy of our reactor and take neutrons out very easily. So we need to be able to keep track of these of these highly absorbing fission products, because if you have a lot of absorption coming into your reactor, that's going to impact your K effective, which is going to affect your power and your criticality state and things of that nature. And so if you, especially for thermal reactors, some of these fission products have very high thermal absorption cross sections in the thermal range. And so when we talked about the pseudo fission product approach, that is really good to group all of our fission products together. But some of those fission products, we want to treat them separately because their absorption cross sections are so high that it's actually worth explicitly modeling those by themselves instead of lumping them with our pseudo fission products. So the pseudo fission products would really be like most of the nuclides that don't have like very large absorption cross sections. And then for the ones that do have really large absorption cross sections, like xenon 135 and samarium 149, we can explicitly determine how those concentrations evolve with time to be able to more in detail and more accurately predict what's going to be the impact of those fission products on our reactors. Um, and the buildup of these products is more on like intermediate time scales over like hours to days of the reactors operating. So this is a plot of some cross sections for some nuclides of interest that we might see in our reactor. So this red line is the total cross section of U-235. This purple line is the hydrogen cross section. This blue line is the total cross section for U-238. This green line is the cross section for oxygen. So if you think about these guys, those are the things that are just like going to normally be found in a reactor. Normally in a reactor, like at startup. And as your fuel fissions and you produce fission products, two of the most important fission products that we produce are samarium 149, which is this guy, and xenon 135, which is this guy. So notice that in the thermal range, going from like here to like about 1 eV, this is the thermal range. And notice that in the thermal energy range, these are, by the way, for xenon and samarium, I've only plotted the absorption cross section. So notice that for samarium and xenon, the absorption cross sections of these guys in the thermal range is like orders of magnitude larger than the cross sections of the materials that are normally present in our reactor. And so, like, when neutrons are in our reactor, they're like all of the materials are in competition for doing things with those neutrons, and the cross section is a measure of like how likely is an interaction to occur when a neutron interacts with these materials. So if you have xenon and samarium in your reactor, the neutrons are going to be absorbed into those very readily, to the point that they kind of dominate over the other materials that we have. And this is just to illustrate why it's important that we keep track of these guys in particular, because their absorption cross sections, are so high. So specifically talking about samarium 149, the thermal energy cross section of samarium 49 is like 40,000 barns, which is larger than pretty much any nuclide in our reactor except for xenon 135. So we need to be able to keep track of both of these. And right now we're going to talk about just samarium 149. The way that samarium 149 comes into our reactors because a neodymium 149 is a fission product. So you have fission reactions. Some fraction of those fission reactions produce neodymium 149. Neodymium 149 is radioactive. It beta decays and has a half-life of about 1.7 hours, where it becomes promethium 149. Promethium is also radioactive, and it beta decays over with a half-life of 53 hours to produce samarium 149. And once samarium gets born into our reactor, the only way that we get rid of it is by it capturing a neutron. Samarium 149 is not radioactive, so the only way that the samarium gets used up is by it itself capturing a neutron with its super large absorption cross section. And once samarium 149 absorbs a neutron, it becomes samarium 150, which is not super relevant to our reactor operation. So once we form the samarium, the only way that it leaves our reactor is by absorbing a neutron. So it remains until it absorbs a neutron. So this is like the decay, like the production destruction chain that we would use to predict what is happening with samarium in our reactor. And for practical purposes, because that half-life of neodymium-149 is so short, we can basically assume that fissions kind of just directly that we have a fission yield that basically produces that neodymium-149. Um, we could basically, or sorry, because this half-life is so short, we could assume that the fission reaction basically just directly produces the promethium 149, and we can just use a yield for neodymium. We could use a yield for that production, which is called the yield for neodymium. And the neodymium yields are given in this table for different fuel nuclides caused that fission due to thermal neutrons. So these are the yields. This is the Y and D values for like if we're using 235, if the fuel is uranium 235, then that would be my yield for neodymium for that fuel. And then we can also further simplify by assuming that when promethium 149 decays, it eventually will produce samarium 149, and we'll assume that the decay yield for that is just 1. We'll kind of ignore the other paths that promethium could have, and we'll just assume that every time promethium decays, it produces samarium 149. So based on those simplifying assumptions, this is what our decay chain looks like. Fissions directly produce promethium with a yield based on the neodymium. Promethium always decays and produces samarium. Samarium 149 absorbs a neutron and eventually becomes samarium 150. So if we assume oh, question? Yeah, samarium 149 would be considered a neutron poison, absolutely. And that's because of this super large absorption cross section that it has. So we're going to use group average values for our fission cross section. We're going to assume a constant flux phi. And we can use this simplified chain to develop production and destruction equations for the promethium 149 in our reactor and the samarium 149 in our reactor. So if you look at promethium 149, these equations are conservation statements. They say change rate equals gain rate minus loss rate. For promethium, it's gained due to fission and it's lost due to decay. So for promethium, it's a fission production and a decay loss. That fission production looks like a fission rate density times the yield for neodymium. Because, yeah, basically saying every neodymium is going to produce this promethium. So if I know the yield of neodymium, that will eventually lead to the production of the promethium I'm tracking. And then promethium gets lost by beta decay. So this is the decay loss density of my promethium. Lambda for promethium times the number density for promethium. And then for samarium 149, its change rate is due to its gain rate minus its loss rate. Samarium is produced every time promethium decays. So for the gain for samarium, it looks like the decay rate for promethium. And the only way that samarium is lost is by it absorbing a neutron. So this right here is the absorption rate density for samarium. And so these would be my governing differential equations. And if I want to solve these differential equations, I just need to know the initial conditions, which would tell me about the initial core composition data for the promethium in my reactor and the samarium in my reactor. And so if we start doing this problem at the beginning of life, when the fuel is fresh, there's no fissions that have happened yet. So there's no fission products that have been built up. So at time 0 at the beginning of life, we can assume that both of these concentrations are 0. If we wanted to solve these differential equations, both of them would involve the use of integrating factors. So we would need to use integrating factors to solve these guys because they are not separable. And if we were to do that, then using these differential equations with these initial conditions, this is the solution I would get for promethium, and this is the solution I would get for samarium. And samarium gets more complicated because I have to take the solution for promethium and plug them in here to be able to solve for the concentration of samarium. So those would be those general equations. On an exam, I wouldn't expect you to derive these equations, but I would certainly expect you to be able to, given these results, do calculations with them, make predictions based on these functional forms. So that's kind of what I wanted to ask about here, which would be if I've started my reactor up at time 0, and then I've ran the reactor for a really long time, like 100 hours, we want to ask the question, what's happening with the concentrations of these nuclides after the reactor has been running for a really long time? And if we wanted to know that, we could take these definitions and then we could take the limit of these equations as t goes to infinity. So we're going to take limits as t goes to infinity. And if I take the limit, if I look at these equations and I take the limit as t goes to infinity, notice that in my functions, the only place where the variable t appears is inside of these exponentials. And what's going to happen to these exponentials if I let t go to infinity? What do these exponential terms do as t goes to infinity? Um, they would go to infinity if they were positive. They go to 0. Perfect. So what I'm going to say is that at time infinity, I'll say the amount of promethium at infinity is going to be equal to, if this is 0, then the equilibrium concentration is just this multiplier that I have up front. So it would look like flux times my fission cross section times my yield for neodymium divided by the decay constant for promethium. So the promethium builds up in a equilibrium concentration that depends on the flux. Notice that this is phi dependent. How much promethium I get will depend on what flux and therefore what power level was my reactor operating at. And for samarium, I'll have the amount of samarium as time gets very large. All of these exponentials are going to go to 0. So for this term, I get 0 minus 0, which is 0. So that knocks out this entire part of the samarium solution. And then the only thing that's left is this multiplying constant up front for samarium. So the amount of samarium that I have is going to look like the fission cross section times the yield of neodymium divided by the sigma A for samarium. And notice that the amount of samarium in my reactor does not depend on flux. The samarium equilibrium concentration is phi independent. So what this tells us is that if we start a reactor up, operated at some power level, at some time in the future, we're going to build up equilibrium concentrations of the promethium and the samarium. I'm going to end up with some plateaued amount of this fission product poison that's going to continuously exist in my reactor as it operates. And if I've built up all of these poisons, I'm going to have to do something to my reactor in terms of changing characteristics of it for the reactor to remain critical as all of these fission products, all these fission product poisons have gotten built up. And if I take that samarium equation and I multiply the absorption cross-section over, then we can kind of see that this equation is telling us that there's kind of like a balance for samarium between it absorbing neutrons and then fission events producing the samarium based on the yield of neodymium. So in terms of like if I had some numbers for like typical reactor values, then I could actually plug them in and I could determine how fast those exponentials actually decay away. And for samarium, those exponentials end up dying out around 300 hours. So what that means is that from time 0 up to about once I get to about 300 hours, we end up building up equilibrium concentrations of the samarium in my reactor. Um, and With that, I had a couple more slides that I wanted to get through, but I'm out of time. So we'll just pick up with finishing the story about Sumerium when we get back on Monday. We will also talk about Xenon as well. So if y'all have any questions for me, please let me know. Otherwise, I hope y'all have a good rest of your day. Hope y'all have a good weekend. If you have any questions, let me know. And if not, take